Thank you very much. So today, as promised, we will introduce and discuss syzygy schemes. So let's just briefly recall what we discussed yesterday. So again, if we have the polynomial ring and we call V the span of the variables, whenever we are given a finitely generated graded module, we have this Koszul cohomology, which is the cohomology at the middle term of this complex, and we saw how these differentials act. And the main feature of Koszul cohomology is that they compute graded Betti numbers. So the elements in the Betti table actually coincide with the dimensions of these Koszul cohomology groups. And the favorite examples come from geometry. For instance, if X is a projective variety, well, usually non-degenerate, we either take the ideal or the coordinate ring, and these two are actually related. I mean, computing Koszul cohomology of the ideal or the coordinate ring is basically the same. Or if we had a projective variety with the coherent sheaf, we could take this module of sections, and then we have the Koszul cohomology of this module, with the notable particular case when F is trivial. So if we had a very ample line bundle which gave an embedding into a projective space, then these two objects are isomorphic if and only if X is projectively normal. So in general, projective normality, I should probably put a note here. So remark, projective normality is equivalent, well, with that fact, but also with the vanishing of K0Q of XL for all Q bigger than or equal to 2. So we can read projective normality from Koszul cohomology, actually. But in general, even if we don't have this condition of projective normality, we still have Kp1 of Sxv is isomorphic to Kp1 of X and L for any P. So if we are only concerned with classes in weight 1, then these two things are isomorphic. So if the the variety X is not projectively normal, things become different starting from the next row. Okay, let's discuss now. So that's about the a reminder of what we have discussed. Let's start. Let's talk about syzygy schemes. So syzygy scheme, it's supposed to be a device that produces. So the aim is to produce non-trivial geometry from non-trivial syzygies. That's somehow the idea behind syzygy schemes, and so far people looked at linear syzygies. So probably I should mention here that we look at linear syzygies, which is we look at the on the linear strand of the Betti table. So we start with quadrics, then linear relations among these quadrics, then linear relations among linear relations, and so on. That's what we do. Okay. So probably the best way to start with is with a relevant example. And this example would be 7-point in P3. And of course you can ask why 7 and not 6, 5 and so on, but we will see that in a moment. So we actually want these 7 points to have. So remember that I mentioned yesterday that semi-continuity is valid if we fix the Hilbert function. So we want to fix the Hilbert function of these 7 points. The Hilbert function should be the Hilbert function of general points, and this is ensured if we suppose that, let's call this x, that x is in linear general position, which means that there are no 3 on a line or no 4 on a plane. That's what it is. And then the Hilbert function is then hx is the following. So we have dhx 0, 1, 2, 3, and so on. So we have 1, 4, 7, 7. Okay. So what's the dimension? The dimension of ix2 is 3 plus 2, which is 2, minus 7 equals 3. So we have 3 independent quadrics in the ideal. What's the dimension of ix3? That's 3 plus 3, choose 3 minus 7, which is 13. And now let's remark that these 3 quadrics generate a 12-dimensional space of cubics. So the dimension of the image of so what's the span of these quadrics is, so V is of dimension 4, this is of dimension 3, 4 times 3 is 12. So that's 12. Which means that the quadrics cannot span the whole space of cubics. So there is 1 cubic left. So we need one more cubic in the so we need at least 1 more cubic in the ideal.
How can you guarantee that the dimension is precisely 12?
Because of the linear general position hypothesis. So they impose independent conditions on quadrics. That's why. So that's the dimension of the space of quadrics on the projective space, and they impose independent conditions. So that's the question was here.
Yeah.
So we have, this is of dimension 3.
Yeah.
And what is so this is of dimension 4.
Yeah.
And this is injective. That's an injective map.
The question is, how do we know that the map is injective?
Well, that's
There may be some physics
among. Well, yes, you're right. Thank you very much. So that's sure. You're right. You're absolutely right. So that's not necessarily injective. So that's at most 12, of course. Yes, that's actually the point. Thank you. Sure. Okay. So that's why we need. Otherwise, yeah. Actually, it was contained here. If it was 12, then we would have needed exactly 1 more cubic. So, but I said, yeah. Sorry for being sloppy. Okay. So the Betti table is is the following. So we have 1, we have, let's put the betas and then compute them afterwards. Beta 1, 2, beta 2, 3, beta 3, 4, beta 1, 3, beta 2, 4, beta 3, 5, and that's it. That's the Betty table. And now we know that the beta 1, 2, which is the number of quadrics, so beta 1, 2 is 3. Okay. Now from the Hilbert function we get, so remember that we discussed that if we take the alternate sum, these numbers can be, the alternate sums can be computed from the Hilbert function. And we know the Hilbert function. So from the Hilbert function, from hx, we get, what do we get? Beta 1, 3 minus beta 2, 3 equals 1. So the difference of these two is 1. And also beta 2, 4 minus beta 3, 4 equals 6. The difference of these two is 6. And finally, the last one, which is beta 3, 5 here. 3, 5 must be a 3. So we have these relations. So in particular, the Betty table is something like this. So 1, 3, then we have beta 2, 3, beta 3, 4, this is beta 2, 3 plus 1, this is beta 3, 4 plus 6, and this is 3. So the question is, what are these? So there are two numbers that we have to discover here. So what are these numbers, beta 2, 3 and beta 3, 4? So that's the question. And the result is the following. So this result is taken from Eisenbach's book. But I think that it goes back to 1915. There is a paper of White. So I don't know, I should quote White, but I'm not sure about it. White, 1915, in Proceedings of the National Academy of Sciences. So he studies 7 points on in P3, and there are equations in this paper. Okay. So if X in P3 is a set of 7 distinct points in linear general position, then there are two possibilities. There are precisely two possibilities. So the first one is when we have no syzygy among these quadrics, and then we have, since we have no syzygies, then the dimension of this one is precisely 12. And then we have one cubic, one extra cubic, and then the others are 6 and 3. Or when there are syzygies among these quadrics, 1, 3, and then there are precisely two syzygies, and then we have 3 here, and nothing, 6, 3. And these two possibilities are distinguished by the following, according to to whether or not or rather I should have exchanged x lies on a rational normal curve. So if it lies on a rational normal curve, then it has this Betti table. If it doesn't, then it has the other one. So probably the correct grammar sentence would have been to exchange the two Betti tables. Okay, and now it's clear why we chose 7 distinct points, because any 6, so 7 is bigger than 3 plus 3, strictly bigger than 3 plus 3, which is 6. And any 6 points lie on a rational normal curve. So that's from this point of view, 6 points are not that interesting. So this phenomenon occurs from at least 7 points on. Okay. Then let's sketch the proof. So first a remark which is going to be useful. So whenever we have an inclusion x in y, then we get beta I plus 1 of y is lower than or equal to beta I plus 1 of x. So if we are concerned with linear syzygies, an inclusion will give an inequality on Betti numbers. Okay, and what's interesting is that the interesting phenomenon here is that it's actually this claim that if there are no syzygies among these quadrics, then everything is cleared. So the Betti table is computed from the Hilbert function. But what's interesting is that if there is a syzygy, then there are precisely 2 syzygies, and that's where syzygy schemes come into the picture. So this phenomenon, I mean, we could have asked, okay, maybe there are 3 syzygies, right, and the 1 syzygy next. But there are precisely 2 syzygies, not more. Not more, not less. And this is, so remark, that's somehow related to the rational normal curve. The Betti table of a twisted cubic, actually rational normal curve twisted cubic in P3 is the same. Of a twisted cubic is the following. So we have 1, 3, 2, and that's it. Why? Because the equations we can, up to the transformation, the equation of a twisted cubic is given by the 2 by 2 minors of this matrix. So we have 3 quadrics, which are exactly 3 2 by 2 minors, and the linear syzygies are obtained just by copying. If we copy this row here and take the determinant, then we have a determinant with 2 equal rows. So that's 0. And then if we develop the determinant, we compute it by developing on the first row, then we get one relation. And the same with the second row. That's how we get the 2 relations. And that's it. That's the Betti table of a twisted cubic. And we see that this is reproduced actually here in this part of this Betti table. So we have the Betti table of the twisted cubic plus something else, which is very, very interesting. Okay, let's sketch a proof. So proof sketch. So we only have to assume that beta 2, 3 is different from 0. So there is at least one linear syzygy among those 3 quadrics. So one linear syzygy among this Q1, Q2, Q3, which span the space of quadrics. So this means that we have three linear forms in V such that L1 Q1 plus L2 Q2 plus L3 Q3 equals 0. And now let's put W, the span of these three linear forms. It's inside V, which is of dimension 4, so that's of dimension 3 inside V. So this relation will give us an element in K12 of Ix, but actually since we have three forms and not four, this is with values in this subspace, in this smaller subspace. Right, that's just by definition, that's an element of the kernel of the multiplication map. So I just wrote down a triviality here, right? That, but now K12 of Ixw is the same as K21 of Sxw. So I stated this for here, but it also holds for smaller subspaces if we work with smaller subspaces. So then this means that there is a gamma in wedge 2 W tensor V such that delta of gamma, so that's the Koszul differential, is precisely L1 tensor Q1, so the element here, plus L2 tensor Q2 plus L3 tensor Q3. And now we can write gamma. We can write it in the following way. So gamma is an element in wedge 2W tensor V. So we can write it as L1 wedge L2 tensor. I need another letter. So probably A is not a good idea. A stands for constants. Do you have a good letter for linear forms? Small l, capital L. Let's put capital L, yes. L12 plus L1 wedge L3 tensor L13 plus L2 wedge L3 tensor L23. Okay. With Lij in V, and let's put Lji is minus Lij. Okay, then if we identify, so if we write down the Koszul differential and we identify, so write the Koszul differential and identify, right? We will have to gather together the elements that correspond to L1 and then identify with what we get with Q1. What we get is that Qj equals sum of small li, capital Lij over I. So That's somehow a general phenomenon. Whenever we have a bunch of quadrics with some linear, that's a very, a general and very useful trick. Whenever we have some quadrics with a linear relation, then we can see this element as in the kernel of some W, where this is the span of those linear forms. And then this is isomorphic to KAIST, the 2-1 of this thing. We write down, we get a class, we write down the Koszul differential, and we can identify Q. And then if we write this properly, Q1, Q2, Q3 are the 2x2 minors of the matrix L1, L2, L3, capital L1, capital L2, capital L3, with L1, L2, L3 determined from this relation. So we can always find a form like this, right? Because, for example, Q1 will be minus L2, capital L12 minus L3, capital L13. Q2 is similar, so we can arrange and get this. And this is so the 2x2 minors are so the 2x2 minors, they give a rational normal curve. So they define a rational normal curve. So the moral is that if we have a linear syzygy and we take these three generators, then we get they define a rational normal curve. Okay.
Excuse me. So
yeah.
How do you obtain the equality in the bond?
Sorry, this one?
Yeah.
Well, if you write down, for example, if you write down, let's write down delta gamma, delta of gamma. What is delta of gamma? This is, by the definition of Koszul differential, this is let's see, L1 tensor L2 L12 minus L2 tensor L1 L12 plus L1 tensor L3 L13 minus L3 tensor L1 L13 plus L2 tensor L3 L13 minus L3 tensor L2 L13. So we just have to add this term with this term, this one with this one, and this one with this one. So we get L1 tensor L2 L12 plus L3 L13. Now for L2 minus L2 tensor what is it? L1 L12 plus, sorry, minus L3 L13. I hope I got the signs right. Now for L3 minus L3 tensor L1 L13 plus L2. There is something wrong here. L13 L2, that should be L23, right? L23, sorry. And L2, there is L2, L3, L2, 3. Right. So this is L2, 3. Okay. So this must be Q1. This is Q2, and this is Q3. So that's why I wrote this here. But we have actually more explicit formulas. And then we can arrange so that this becomes exactly the minors of the 2x2 minors. For example, if we take, let's see, so L1, L2, L3 are exactly L1, 2, L1, 3, L2, 3, but with some signs and maybe mixed up. So we have to be careful how to arrange them to get exactly the 2x2 minors, because these are actually 2x2 minors. That's why I wrote it this way. Yes? Okay. So what we did was we started with a linear syzygy and we constructed geometry out of this linear syzygy. So we constructed a curve which contains, so the moral of this result is that beta to 3 different from 0, then there is a rational normal curve C containing our set of points. That's what we did. Out of a non-zero syzygy, we constructed geometry. So we managed to put these points on a rational normal curve. So that's what syzygy schemes attempt to do in general. So this phenomenon generalizes to syzygy schemes. So I think I can erase this. So in general, what we will do, out of a non-zero class in KP1, so that will be a non-zero beta p plus 1, we will construct a larger variety that contains X, and in some cases we can classify these varieties, which and these varieties have very special geometry. Like they tend, so the tendency is that there is no proof of this general fact, but the expectation is that, or the tendency is that they have small degree. So either minimal degree or 1 plus minimal degree. So they somehow what we try to do is to, out of some interesting nonlinear syzygies, we construct varieties of small degree that contain the variety X, and this will give non-trivial information on the geometry of X. And let me give you a sample. That's a theorem proved by Green in 1994. It's called strong Castronovo lemma. Yes?
Can you say something about the dimension of that larger variety if we choose?
No, I'm afraid not. So it's very hard, and there are very few cases where this is explicitly known. So in general, it's a completely open field. So because it's very hard projective geometry, but anyway, any new result which would come in this direction would be very interesting.
You consider one single element, single non-zero element.
Sorry?
So you choose one non-zero element alpha.
Yes.
Then construct one
variety. Yes. Yes.
So we may take the intersection of two.
Yeah, that's what we also do. But in the extremal cases, just taking one suffices. I mean, they all coincide, so the intersection is the same. But in general, we will have to take the intersection, of course, to get something more interesting. I will come to that a bit later. So that's strong Castel Novo Novo lemma. And it says the following. So suppose X is a set of D, at least n plus 3, distinct points in linear general position in Pn. Then Kn minus 1 of X is different from 0 if and only if X lies on a rational normal curve. Well, of course, for n plus 3 points, it's automatic that it lies on a rational normal curve. But for larger, we need this condition. Like in the previous case, we had 7 points. And it's exactly this statement. N equals 3, 3 minus 1 is 2. So this is beta, the dimension is beta to 3. So beta to 3 is different from 0 if and only if it lies on a rational normal curve. So that's precisely the generalization of the previous fact. So the terminology comes from the classical Castronovo lemma, which said that if you had at least 2n plus 3 points in Pn that impose at most 2n plus 1 conditions on quadrics, then they lie on a rational normal curve. So the Castronovo lemma was about points on rational normal curve. But this is, I mean, the nature is slightly different because that's about connecting syzygies and geometry.
From means they cover n plus 3 to 2n plus 1 between them?
Yeah. So also the degree is much smaller than in the classical Castronovo lemma.
Yes.
In the classical Castronovo lemma was 2n plus 3.
Yes, 2 plus 3.
Yeah, and this is n plus 3.
Yes.
Okay. So for the so the proof uses syzygy scheme. So it's now time to give the definition of the syzygy scheme. So that credit should go to Green, but Green didn't call it like this, but he was the one. So he called them varieties from multilinear algebra, something like that. But then the terminology is due to Schreier and his students, Ibauer and von Bottmann. But it's mainly due to Frank Schreier. So let's assume let P bigger than 2 and alpha different from 0 an element in wedge P of V tensor V. So we know that this give classes, causal cohomology classes. So would it be okay if I go a little over time today? I mean, at least this morning to finish. So I promised you a proof of Green's lemma, so okay. Probably it's better to give it this morning. Okay. And then we can make a shorter talk in the afternoon, probably. Okay. If it's okay with you. Okay. So now we apply delta of alpha. So once again, that's the causal differential. This is in wedge P minus 1 of V, tensor S2 of V. So that's polynomials of degree 2. And let's write this delta of alpha. So it will be a sum of xi. So xi is xi1 wedge xi P minus 1 over all the multi-indices I, capital I, tensor, here we have some quadrics Qi. So if we start with such an element, then we get, just by applying causal differential, we get a bunch of quadrics. So the scheme defined by this quadrix is called the syzygy scheme. So we syd P of alpha, P stands for this P, is given by the vanishing of all these of all these quadrics. So this is in Pn. We call syzygy schemes because we don't know whether actually in general they are schemes or variety or what they are. But in the most relevant cases they are actually varieties. So implying that also the ideal generated by Qi is saturated and so on. So this is reduced, I mean all the good properties. So this is syzygy scheme. So once again, we start with an element, then we apply causal differential, we get some quadrics. But these quadrics are, I mean, if we apply once again the causal differential, then we get 0. So these quadrics are not any quadrics. So they come equipped with some linear relations, like for the rational normal curve. They have relations among them, so they are not independent. So they are a sort of special quadrics. And now let me remark that if we change alpha by an element coming from wedge P plus 1, then delta of alpha doesn't change, so Qi doesn't change either. So the syds P alpha doesn't change if we modify alpha by a class in wedge P plus 1 of V. So it only depends on classes in or on its class in wedge P plus wedge P V tensor V mod out wedge P plus 1 of V. So syzygy schemes only depend on these classes. So we can mod out this one. And now a very important remark, which will be used very often. So if these quadrics vanish on the coordinate points, so if Qi of 0, 1, 0, and so on equals 0, so if these quadrics vanish on the coordinate points, then something interesting happens. So let's just choose a quadric which vanishes on a coordinate point. Then this quadric will say Pj. This quadric will not have xj squared in its expression. But not only this, so not only that they don't have expressions like xj squared, it's also that Qi, any Qi only depends on variables xi with I not in I. So somehow it depends on complementary variables. And that comes from the fact that we have relations. So that's why is it so that delta squared equals 0 when we apply to alpha. Then we apply delta to this element, and then we get the element 0 equals the element, the sum, if we write carefully, is minus 1 k not in the set k1 kp minus 2 minus 1. Now we have to count the numbers of j's lower than k, xk times q k1 k kp minus 2. So this is 0. That's the differential. It looks horrible, but this is what it is. So the differential is applied to that element is just this this thing with some factors behind. So that's what corresponds to the multi-index k1 kp minus 2. So in particular, if we stare at enough at these relations, we see that so q k1 k kp minus 2. So if this depended on xk, then this expression would contain xk squared, and we cannot cancel out this expression from the other quadrics. So we just have to be careful a bit about knowing that all these qi's don't have squares as monomials. Then we have to be careful to see which can cancel which. So, and yeah, that's basically what it is. So we have to pin this this fact. So if we have coordinate points in the syzygy variety, if these coordinate points belong to the syzygy variety, then these qi's will depend only on complementary variables. Okay. And in general, we will consider these classes coming from syzygies of other varieties. So what we'll consider, so that's a general definition. It only depends on an element in which P of V tensor V. But now if this defined in general, we will consider classes coming from Kozul cohomology of a variety X. X can be a bunch of points or a curve or whatever. So what does it mean? So this means that these QIs vanish along X. So i.e. these QIs will vanish along X. And then X is contained in the syzygy variety. And not only these quadrics will also define a syzygy of the syzygy variety. So if we call this Z, I said syzygy variety, but it's actually a scheme for the moment. So if we call this Z, then alpha will give a class in KP1 of S, Z, and V. And that's somehow the largest scheme for which alpha is defines a syzygy, defines a Kozul class. Okay, and let's see some simple examples. Now, probably I should keep maybe I can erase there. So, examples. The simplest example is a twisted cubic, CMP3. Twisted cubic. Then we have the Betti table is 1, 3, 2. These are the three quadrics, and these are the two linear relations. So if we take a class different from 0 in K to 1 of C, Then the syzygy SIDS2 of alpha is actually C, coincides with C. And why is that? So if the equations are the 2 by 2 minors, x1, x2, x0, x1, x2, x1, x2, x3. So these are the equations with the known relations. And then alpha will give an element L1 tensor Q1 plus L2 tensor Q2 plus L3 tensor Q3 in the kernel of the multiplication map V tensor I to C, sorry, to I3C. And if we write Li as a combination of xj's, then we get the quadrics from the definition are just combinations of Q1, Q2, Q3. So the quadrics from alpha are linear combinations of Q1, Q2, Q3. And they are independent. So they give the same, so let's call this Q1 prime, Q2 prime, Q3 prime. So they give the same zero set as the original quadrics. Now a sub-example which we saw in the previous result was that if we have x to be 7 points in P3 and alpha different from 0 in K21 of x, then SIDS2 of alpha is a twisted cubic. Is the twisted cubic we found. So these are somehow the first and simplest examples we have. And now this generalizes as follows. And this is where can I erase? Probably this one? This one. So we know now the definition. So let's prove the following theorem, that if C is in Pn, is a rational normal curve, and alpha different from 0 in Kn-1, 1 of C, then SIDS, the syzygy variety of alpha coincides with syzygy, that's right, it coincides with C. So let's give a proof of that, because it involves a very nice monodromy argument of Green. Okay, and let's first recall that the minimal resolution of the homogeneous coordinate ring of C is, or of the ideal is the same, is the following. I see S of -2. We have n choose 2 copies. So we have again, like in that matrix, but you imagine that we go, instead of 3 columns, we have n columns. And we have again the 2, so the equations are given by the 2 by 2 minors. Then we have a sort of similar relations obtained just by copying the rows. So these are linear relations 2 n choose 3, and so on. The last one would be s of minus n, and we have n minus 1 n choose n, which is n minus 1 actually copies. So we are looking here at syzygies at the extreme. So it would be okay if we proved that the number of quadrics, that the number of independent quadrics involved in alpha is at least n choose 2. Why? Because remember that if we start with the Koszul cohomology class of a variety, then all these quadrics will vanish along this variety. So if we have and the ideal of the curve is generated by n choose 2 quadrics. So if we have n choose 2 quadrics among these n choose 2 quadrics, then they must generate the same thing. So the goal is to prove that the number of independent quadrics is bigger than or equal to n choose 2. It's actually equal. Okay, and we will use two facts. So one fact is restriction. So we use two facts, which I will point now. If M is a finally generated graded S module, and we choose the minimal resolution, minimal free resolution for M over S, and then take L in V, so a linear form, which is a non-zero divisor for M. Then M mod Lm F tensor over S, S tensor L is a minimal free resolution of M Lm over S mod L. Yeah, that's a polynomial ring. This is a linear form. When we mod out, we get another polynomial ring in lesser variables. And that's a module of this polynomial ring. So, the syzygies are preserved. The moral is that the syzygies are preserved when we choose hyperplane sections which correspond to linear forms which are not zero divisors for the module. So that's somehow the very brief proof idea is that, well, that's certainly minimality means that we don't have in the matrices, we don't have constant non-zero terms. Well, these are preserved here because what we do, we just cancel, we reduce modulo L, so that's preserved. It's free because these are free modules. When we twist, we obtain free modules. So the only thing left is to prove that that's a resolution, exactness. But to prove exactness means that, well, that's where you use that this is not a zero divisor for M, because if you start from M, then you take the kernel, you twist by this guy, then you get a long exact sequence continuing with Tor 1 of M and S over L. And Tor again is symmetric, so you can compute it either way from the minimal resolution of M or from the minimal resolution of S over L. And it's very easy to write down the minimal resolution of S over L, which is just 0 goes to S of minus 1 S over L. So if you twist this by m, then you get exactly the condition that if it's non-zero, then tor 1 is 0, and so on. So the fact that this is non-zero, then it ensures that this is exact when you twist.
Can you apply this to the
This can be applied in any situation.
projective right case?
Yes.
How can it interpret?
Well, if you take the hyperplane section, where you need to take a general hyperplane section, right? Then the Betti numbers are the same. If you take a non-degenerate variety and irreducible, you take a generic hyperplane section, then the Betti numbers are the same.
Yes, but that is not exactly the same as homogeneous codating of the section.
Yeah, because you have a problem with whether the ideal is the ideal of a section, right? That's
yes.
Yeah.
But m quotient n times m is not the homogeneous ring of hyperplane section.
Yeah, I know. Yeah, but this will apply here to this situation. Okay. Maybe I can erase here now. But in our case, that's true, because if you take L, so we have for L in V general, what we obtain is that for L in V general, we are actually interested in KP1s, and if we take Y, say L to be C intersected with VL, KP1 of YL, or let's put like this, is isomorphic to KP1 of Y of C. So by the restriction we get this isomorphism, and that's what we are going to use. And so the result will follow from the following claim. Let's write Qi for the quadrics involved in the class alpha, and suppose that the coordinate points so P0 up to Pn belong to C. So in particular, these quadrics vanish along the coordinate points because they all vanish along C. Then Qi is different from 0 for all I, and moreover Qi will have this expression sum over K and L not in I, AKL I, XK XL. So remember that we said that if the coordinate points, if the quadrics vanish along the coordinate points, then the quadrics only depend on complementary variables. So that's what I wrote here. But the important thing is that with AKL I different from 0 for all K and L. Oops. So this is the claim. So let's prove the claim, or let's assume that the claim is. Let's take the claim for granted for the moment, and then let's prove the claim, and see how the claim implies that the number of quadrics is at least n plus n choose 2. So if we take the quadrics for lambda and mu with lambda lower than mu, if we take I lambda mu to be 0 n minus 1 minus lambda and mu, then these are the quadrics qi lambda mu over lambda and mu are independent. Why are they independent? Because the coefficient, so x lambda, x mu, occurs in qi lambda mu with non-zero coefficient and does not appear in the others. So we get exactly n choose 2 independent quadrics. So if we had this claim, then the strong Castronovo lemma would be no, sorry, this theorem would be proved. So maybe I can erase the statement now, and let's focus on the claim. And we will stop after, and we continue in the afternoon with the proof of strong Castronovo lemma from this theorem, using this theorem. Okay. So the proof involves a monodromy argument, which is the following. Is due to Harris.
The coefficient are not 0, but it's not the same?
No, they are not the same. That's the point.
They are the same or not same?
They are not the same. They are only all different from 0. But they are not the same. They might be the same, but in general they are not the same. And I will explain. I will try to explain why they are not the same. So that's that's somehow the key point in this result. So we take these quadrics which are involved in the syzygy, and they are either, I mean, they are all different from 0, and all the coefficients are different from 0. Okay, how this monodromy argument works? So the monodromy says that if you take the set xh in C times P and dual, that's the incidence with x in H, and you take U to be the set of hyperplanes that intersect C transversely, in n distinct points. Then the monodromy group of I to U is the full symmetric group. What does it mean? It means that So this is equivalent actually to the irreducibility of I. But what does it mean geometrically? It means that if you take a loop, you start from a hyperplane section, and you take a loop of hyperplanes. So you start from here, you take a path, and you return to this hyperplane section. Then you get a full symmetric group. So if you want to permute, so you take a hyperplane section, so you have endpoints in the hyperplane section. There is always a loop of hyperplane permuting these points. So somehow, from the intuitive point of view, what you do is that you have this bunch of points, and you move slightly a hyperplane such that one of them moves away. Then you move another one away, and you move this back to the original one, and this one you move it to the other one. Somehow you can permute points. And then you can do the same for all the permutations. You can transpose points, sorry, yeah. So this means that we can move along a loop of hyperplanes starting from a hyperplane section and permuting the points however we want to do them, to permute them.
The permutation gives some restriction on these variables if you apply it?
Yes, that's what it means exactly. So how does it act? So we have, so let's assume now that n is in some I, and put h to be v of xn, and take a loop of hyperplanes. Take a loop of hyperplanes let's call ht to be v of lt. So y t to be ht intersect with c. h0 is h1 equals h. So we start from h, we take hyperplanes, and we go back to h. So y0 will be, y1 will be the coordinate points p0, pn minus 1.
Complete?
No, because the degree is n.
I see, it's
Yes, yeah. So you can apply in general for bigger degree, but I just want to prove, I mean, the same argument applies in general. So if we understand this argument, then we can apply it for other curves as well. Then we have restriction maps. So put rho t from k n minus 1, 1, c to, which are isomorphisms, to k n minus 1, 1 of y t. And our alpha lives here. So our alpha restricts to, when we start to move along this path of hyperplanes or hyperplane sections, this alpha will give some alpha, how to call it, alpha bar t in here. But so imagine that, so we have this loop of hyperplane sections, and we have these restriction maps. Alpha bar 0 will be alpha bar 1, because it's just the restriction. It's nothing but the restriction. Correct?
What is alpha 1?
It's for time t equals 0, and this is time t equals 1. So this loop of hyperplanes, so t is in 0, 1.
Yes.
So the start and the end point are the same, are this h. So we start with the same hyperplane section, which we can assume, if we change coordinates, that it's coordinate points in Pn minus 1. So, and now we start to slightly move around this loop.
So alpha t bar is always will define the end isomorphism.
Yeah. Yes. And alpha 0 and alpha 1 will be the same, because they are restrictions of the same class alpha.
Yes.
But on the other hand, moving along this path will have some effect on the Kozulko homology here of the hyperplane sections, because this action of the monodromy will mix the points, will exchange the points, right? So this will permute the points. So that's so the loop. Let's take a loop. Let's call this loop gamma. So gamma will permute the points P0, Pn minus 1. And what's how is it realized? It's just by exchanging variables, right? I mean, if we permute P0 and P1, if we just exchange P0 and P1, how is it done? It's done by exchanging variables x0 and x1. But this is not quite correct. I mean, permuting 2 points, because we work with homogeneous coordinates. Homogeneous coordinates do not see multiplications. So 1, 0, 0, 0 is the same as 2, 0, 0, 0 is the same as lambda 0, 0, 0. So what is one transformation that permutes P0 and P1? Is it a transformation that maps x0 to a multiple of x1 and x1 to a multiple of x0? For example, 0, 1, 2, 0, that's a legitimate transformation that exchanges P0 and P1. Like 0, 1, 1, 0. But this just multiplies the second variable by x1. So the action of the monodromy on the level of variables, it will be that it permutes variables, but it might multiply the variables by some scalars. So it doesn't just mix the variables, it mixes the variables up to multiplication by some scalars. So the action on the action on xi's is by permutation plus multiplication. Possible, maybe not. Maybe we don't need this multiplication, but we don't know. So this depends very much on the loop we choose. So maybe imagine that there is a loop of hyperplanes that exchanges P0 and P1. There are several loops that do the same thing, but one might simply exchange x0 and x1. The other one might multiply x0 by 2 or 2 and move it to the position of x1. So plus multiplication with non-zero scalar. Okay, and we have to understand now what's the action. So this monodromy will act on alpha 0. So it will transform alpha 0, but the transformation will not change alpha 0 actually. And this is why we would get the claim. So let's understand the action. So to understand the action of monodromy on kn minus 1, 1 of y, let's focus on a transposition. Say the transposition 0, 1. Let's just try to understand this, because if we understand transpositions, then we understand everything. So Qi, the bunch of quadrics involved in alpha, were these were some KLI, XK, XL, where K and L are not in I. Now these maps are given by restriction. So we want to understand how the monodromy transforms the restriction of alpha to the hyperplane. So alpha was sum of xi tensor qi, where the length of I is n minus 2. Now what is alpha restricted to h? So h is given by the vanishing of the last variable. So we have to kill everything which involves the last variable. So we take multi-vectors that do not involve the last variable, and we have to restrict the corresponding quadrics to H. Okay, and then if we write Qi restricted to H, this will be the sum K and L not in I, K and L lower than or equal to n minus 1, AI KL, XK XL. So these are the restrictions. So I've written the restriction of alpha to the hyperplane, to the original hyperplane H. Now let's try to understand the action of this transposition on what does it do to the class alpha restricted to H. So the transposition will exchange x0 and x1, right? Up to multiplication by a scalar. And there are three cases. So the first case is when 0 and 1 is in I. Well, if 0 and I is in I, then the transposition does nothing to Qi, because Qi does not depend on x0 and xi. So it does nothing to Qi. So Qi is left unchanged. So for these i's which contain 0 and 1, there's no problem. The second case, if 0 and 1 is contained in the complement of I, then these variables, so it will, Qi will depend on x0 and x1. So x0 and x1 appear in the formula of x, and then of q, and then xi tensor Qi restricted to H will be mapped to xi tensor Q prime I restricted to H. And now let's remember what this permutation does to variables. It will map x0 to a multiple of x1 and x1 to a multiple of x0. So this means that it will so this Q prime I restricted to H will be a sum of AI sigma k. Sigma is just the transposition 0, 1, sigma k sigma L, xk xl, And they are not quite the same coefficients because x0 might be sent to a multiple of x1 and x1 to a multiple of x0. We will just put a tilde there, and a tilde is a multiple of a with the corresponding coefficients. So that's how this quadric is changed.
Okay, there is not 0, 1, then it's same.
Yes, of course, they are the same. If this is not 0, 1, then they are the same. But if one is 0 and the other one is something else, then this one is the same, but the 0 will become 1. And the 1 will become 0. And there will be possibly a multiple from the exchange of variables. So everything is a play with this variable change. And finally, the last possibility is when one is in I and the other one is off. So the third case is when 0 is in I and 1 is not in I. And of course the symmetric case when 1 is in I and the other one is not. And then we can write Q0 blah 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 to be the sum A I K L X K X L, where K L is not in I, K L is not in 1n either. So Q0 and something else, 0 is in I, that's why we put 0 here, will not depend on x0, but it will depend on x1. And we separate what depends on x1. So that will be plus a sum of L not in I, L different from 1 and n, AI 1L x1 xl. So we separated the x1 from the others. And then x0 wedge blah 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 tensor q0 dot 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 will be mapped to x0 is exchanged with x1 tensor q prime I. This is restricted to h. Yeah, that was restricted to h. Where q prime I now is obtained replacing x1 by a multiple of x0. So q prime will be this part here, which is the sum of the first sum plus the second sum will be L not in I, L different from 1 and n. And then we will have AI 1L tilde, again with the same convention that tilde is a multiple, but instead of x1 we will have x0 xl. And now remember that these are all restrictions. And so the class we start with and the class we end with must be the same, because they are restrictions of the same class alpha. So now we just have to equal this starting class and what we get by applying the monodromy action. And if we do that, we realize that we can, just applying permutations, we can send any quadric Qi restricted to H to any other quadric Qi, but with some modifications. The coefficients could be multiplied by some constants, some constant factors. But this multiplication will not affect the fact whether this was 0 or not. So the moral is that if one of them is 0, then all the others must be 0. And if we look now here, what it does, so if we choose a permutation that fixes a given I, we will see that also inside I, inside Qi, the coefficients will be mapped one to another, up to multiplication again by a scalar. So the moral is that if we have one coefficient which is 0, then all the others must be 0. And hence the claim is proved.
But in the second part, this is not now here. 0 is contained in I, so that is not.
0 is contained in I. Okay. 0 is contained in I.
But now 0 is not correct.
You're right. You're right. You're right. So what does it mean? You're actually right.
So now x0 does not occur in the
original.
In the original one.
So because the which starts from x1, which blah 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 tensor with q prime. So we should rename the q prime.
So that would mean that the A1L must be 0? Is that the meaning of...
No, I don't think so. So we should rename the index set. So now we have another...
No, wait. No, it's fine. Because the index will be changed.
Yeah, so
and now this corresponds to the new index. Yeah, we have to re-index. Yes, of course. We have to re-index. We have to keep the indices.
So index also changed.
The index also changed. So they are somehow mixed up, these quadrics.
So of course there are another kind of index set I prime which contains 1 but does not contain 0 will change.
Yeah, I should have said that. Yeah, I should have put a prime here. That's much better. With the prime is now obtained by replacing 0 by 1. Yes, that's now it's correct. Yes, thank you. And now it's everything correct. So the idea is again to understand what does monodromy do to the restriction of these classes. And keep in mind that if we exchange 2 points, this is done by exchanging variables up to multiplication by something. If we exchange 2 points. That's why, so in general, it's impossible to say what is the actual action of the monodromy on a class. Because, in my opinion, it depends very much on the path of hyperplanes you choose. So the transformation, I mean, you can have different paths exchanging 2 points, but they can act differently on variables. And this is not controllable. The only thing that you can say is that whenever you have something which is non-zero, then the other will be non-zero, which is obtained by monodromy. Okay, so I think I'll stop here. So it took a lot more than...
Thank you very much.
Thank you.